to remind. Okay, so just one quick question is if the energy is high, the energy is, I mean, higher, whether it will be a strong bonding or weak bonding. If the energy is very high, what do you think? It will be a strong bond or weak bond? Okay, one question, strong bonding, strong bonding. All right, good. So here, for this thing, potential energy for the two bonding is very high. All right, I go for full screen mode. Here the potential energy is, as I go up, it is very high, and then here it is low potential energy, right? So when the sodium and chloride is coming below their radius size, this is below, I mean, less than their radius, what their radius totally, I mean, allowed them to be there. They are much closer than their radius should allow them. So this is the potential energy is growing high, and that is why they will not form a bonding, or the bonding will be repulsive attraction, or that will be not a strong bonding there. But in this case, the potential energy is very low, the lowest potential energy it should have, because they are exactly at their radius distance, exactly at the radius distance, and that is why negative 589 potential energy. Okay, so that is why it is low energy. But here the potential energy is zero. Why this is becoming? So potential is zero because almost zero, not exactly zero. Zero is on this line, but here is less than a little less than zero, because they have moved from apart from their total radius. Total radius is, I mean, whatever this radius is, they have moved away from there, and that is why they do not have attraction, or less attraction they have between them. So that is why the less potential energy is the higher the bond strength. It doesn't mean that the lower the radius, the potential energy will be lower, no, but at the same radius distance. Now I am your question, you say that just now some of you have replied, strong bonding, strong. As I understand what you mean, that the more the energy, the higher the bonding will be strong, right? So for this case, which one will be higher to break? Which one will be higher to break? What of the bonding will be higher to break? They already have some repulsive energy here. So they repel each other. They don't want to stay together. They already want to repel to each other. I don't like you, like that. So it is very easy to break that, right? Here as well, they do not have that much repulsive energy, but still they are not that in association, so you can break it easily. But here, the potential is very negative, highly negative potential energy, and that is why you have to put more energy to go to overcome this, to go to zero and then go to positive side, then only it will be repulsive and then break away. So this is why that is called that dissociation energy. All right. So my question was half that I should have asked you. The dissociation energy is higher, then only your answer will be correct. But my question was not the dissociation, the bond association energy, potential energy of the bond. How much? Okay. And of course, we can find from this equation that what is the strength of electrostatic forces, and Q1, Q2 are the charges in Coulomb, and then internuclear distances. From here, we can find out what is the bond energy would be, and bond dissociation energy could be high. I mean, which bond will be easier to form or to break if we know this, if we remember this equation. All right. Lewis dot structure, that previous class we were discussing about the Lewis dot, that we would just put a dot on the no, why I'm doing this. Okay, we'll put how is it? I cannot find the eraser. Okay, Lewis dot symbol for aluminium and oxygen. We have seen Lewis dot from the last class that valence electron will be shown as a dot, right? So one dot sodium, that means sodium has a valence electron of one, only one, right? And potassium as well. What about chlorine? Chlorine will be 7 dots shown because there are 7 electrons at the outer shell, or the valence shell electron. There are 7 electrons. Oh, this is chlorine should be, right? Not C. Okay, C. So this is should be chlorine. So 2, 4, 6, and 7. And this is how I will be showing the Lewis dot symbol for aluminium and oxygen. Aluminium in group 3A. All right. And or you can say is 13. Modern periodic table, it is in 13. So there is 13 total electron and then 3 electron at the outer shell. The total outer shell electron is 3. This is nothing. So there are 3 electrons at the outer shell. Group 6A element is oxygen. So there are 6 electron at the outer shell. And then how do they get into association, or how do they make the bonding? This is 3 here, right? This is 3 here, and this is 6. This is 6 in here altogether. So how do they form the association or make the bonding? By the way, this is a mineral corundum, aluminium, alumina. Actually, is aluminium dioxide, dialuminum dioxide. So this is a mineral. It looks like this is a metal. Metal aluminum can be extracted from this type of mineral. And by the way, do you know that aluminium was more expensive than gold in just 100 years ago? Like if you have noticed that Washington DC, there is on the Independence Tower, they have a pyramid of very white metal, and that is aluminium. 18 something, 1840, 1860. That time aluminum was very expensive because it is widely available everywhere, can be found. This is the most abundant material. Metal, in fact, on Earth, but the problem is back that time we did not know how to extract the aluminium from this aluminium ore, and the extraction process was very expensive. That was why aluminium was very expensive material, and long before people used to make ornaments, jewelry with aluminium, not with gold. Of course, gold is expensive, but aluminium was even more because gold can be extracted. People knew how to extract this. Aluminium, they didn't. Okay, anyway, so but afterwards, when the smelting process was invented, aluminium becomes cheaper because it's so abundant, it's so much we can on Earth. So aluminium, so 3 electron here and 6 electron there. So oxygen will need, how many electron oxygen needs to get it octet? Oxygen needs just another 2. Oxygen needs just another 2. Hold on. Oxygen is just another 2 electron for them to get it octet. So oxygen is another 2 electrons for here and here to get it octet filled up. Octet filled up. But for aluminium, P cannot even erase now. For aluminium, it needs how many? Yeah, 2, 3, so 6, 7, 8. Yeah. So it needs 1, 2, 3, 4, 5. 5 more electrons, isn't it? Aluminium will need 5 more electrons, and oxygen will need 2 more electrons to make itself octet filled up. Is it? It's not. So students used to make mistakes sometimes, and that is why I'm telling you that don't do it. It is a mistake. Aluminium is incomplete octet, so it will not take 8 electrons to fill up its octet. It just takes 6 sometimes. So here for this case, 2 aluminium and 3 oxygen atoms. All right, so 2 aluminium and 3 oxygen atoms, they are in association, and aluminium, of course, they will release all 3 electrons. Aluminium will release all 3 electrons so that it becomes easy and fill up its octet. So here they do not take the electron, rather they release. Oxygen will release because it is a metal. And aluminium is a metal and oxygen is non-metal, so it will accept an electron. So here now to fill up, aluminium will give all these 3 electrons, and 3 electrons, oxygen needs only 2 of them, so 3 oxygen atom will take all 3 electrons from 6 electron from 2 aluminium, so that aluminium is getting 3 positive, all 3 oxygen is getting 3 negative, and that is how this aluminium oxide is poured. And in this case, both of them are getting neon structure. It is getting neon structure by shedding extra 3 electron from aluminium. It is getting neon, and oxygen by taking another 2 electrons, it is getting to 10 electrons, so that is neon as well. And this is by definition is also ionic bonding, because aluminium is shedding the electron and oxygen is taking the electron, so there is a electron transfer between them. And also one is metal, another is non-metal. So by definition, metal and non-metal, when they form a bonding, it is a ionic bonding. There's one question here. Is the electrostatic force between aluminium oxide, alumina and oxygen, and stronger than that of sodium and chlorine? Will it be more stronger? Somebody, can you guess? Anybody want to guess? Is it stronger, or it is the same, or is it a weaker? This is a oh, I have some Menti question, of course, for you guys. Later on, we will find out the Menti question, but first let's answer this problem that how many of you think that it will be stronger, and how many of you think that it is not a strong force? Some of us, I think, Chio and Kong says stronger. Audrey Stephanie also said stronger. Do you have our explanation for this? Why do you think that it is stronger? Or why somebody thinks that sodium chloride is stronger? Let me bring out my Menti question here. By this time, please, can anybody answer me? Why do you think that it is stronger? Or why somebody thinks that the other one is stronger? Okay, I'm ready with my Menti question. Okay, so can anybody tell me why this is? Why do you think that it is going to be stronger force, stronger bonding, or just try? Otherwise, I'm going to tell you. Just let's try whether it will be strong force. Or why is it stronger than sodium chloride, or sodium chloride is more stronger? Both are, there is metal and non-metal, right? Both there are metal and non-metal. Both there is electronic strong, ionic bonding is happening between them, and yeah, similar nature. And one is, of course, very hard metal. One is soft metal. Sodium is soft metal, alkaline earth, alkaline metal, alkali metal. Anybody wants to guess? Okay, the time is going very fast. So the thing is, aluminium is metal, oxygen is non-metal. What is the oxygen is electronegative first, more than chlorine, and then almost similar actually. And aluminium is a metal, so it is the electronegativity is less. So the difference is quite high first. Second is there are 3 atoms of oxygen and 2 atoms of chlorine, aluminium are involved in this, and quite many of the electrons are being exchanged. So 3 and so many electrons are exchanged, right? So that is why this, and because of these 3 atoms of oxygen, 2 atoms of aluminum are attached, so that is why they are much stronger bond. All right, for sodium chloride, it is ionic bond as well, but sodium and chlorine, although the electronegativity difference is quite high, but there is only 1 atom are being, 2 atoms are being involved here in this, and that is why it will be a less stronger than aluminum oxide. So properties of ionic bonding, and mostly ionic bonds, those those compounds as ionic bonding, mostly they will have this type of properties, but not always. There is always exception, you know already for chemistry, right? So properties of ionic bonding compounds is they will be crystalline solid, mostly, not always, crystalline solid at room temperature. The general properties, crystalline solid. So do you see the sodium chloride in your kitchen? If you look at the sodium chloride in your kitchen, you will see that it looks like a broken glass, right? A glass dust. It looks like a sugar. So that is a crystal the formation from there. Solid sodium chloride. Okay, and most of the compounds are ionic compounds are of similar nature. For physical properties of similar nature. So they will be brittle. They are brittle. In fact, they easily break down, but not all brittle are ionic bonding. All right, ionic bonds are brittle, but not all brittles are ionic bonding. So high melting temperature, because of their nature of electron transfer or electron sharing, not sharing, sorry, electron transfer, and that is why they will have a high melting temperature. It's very hard to make them smelting or dissociate. Electrical insulator when in solid state. So sodium chloride, let's say, the easiest example in front of us we have that when it is solid form, when it is sugar, dry sugar, it will not conduct electricity through it. It will not conduct electricity through it. But if you dissolve it in water, that water is very much conductive. That water will be very much conductive because of their ability to separate in charges. So when they are in solid state, they are in crystalline solid, and they are sodium chloride together. They do not carry the charges that time, but when you dissolve in water, they are not in crystalline state anymore, and they dissolve and they carry one sodium and another one is chloride charge. So sodium will be positive charge, chloride will be negative charge. Since there is a charge difference, the electrons can pass through, because electrons, they are also charged, right? So they can pass through, and that is why it is easier for to conduct electricity when they are in dissolving aqueous solution. So properties of ionic solids that we already have discussed. Now we go to the covalent bonding according to Lewis structure. Covalent bonding by sharing of the electrons. None of them are taking it or snatching it away or taking the 100% or 99% towards itself, but almost 40 or 45 or 50% towards, sharing to. One is 45%, another is 55% sharing. So that is why the covalent bond, that is called the covalent bonding. All right. For why it is happening, or why covalent bonding? Simply because they do not, the atoms involved in this type of bonding Simply they do not have enough power or enough capability to take one electron away from another one, just like ionic bonds do. They just take away electron from one another. So since they do not have that capability, they go and form a bonding in association with and makes a friendship. All right, so that is why it is a covalent bonding. And for this carbon here, as it shows in this example, that carbon and there are 4 hydrogen are here, right? So 1 carbon and 4 hydrogen are here, so that carbon and hydrogen all, so for carbon, if we look in the periodic table, I should bring one periodic table as well, so that it is easier for us to navigate. Oh, yep. So if we look at the carbon, we will see that carbon has 4 electrons at the outer shell, so it needs another 4 electron to get to neon structure. So it will, but it does not have that much electronegativity. It does not have that much electronegativity. I mean, it does not attract the electrons from that strongly. This is one question for you guys, that why carbon does not attract the electron just like chlorine does. Okay, yeah. This is my question actually. Hello, you guys listening? You guys listening or not? Anybody wants to try? Did anybody try? Yeah. So I mean, yes. Do you want to try? I'm not saying that give me the answer. I'm saying that just try. Why carbon does not have that much electronegativity, just like chlorine or fluorine or oxygen has. You just have to tell me what what is the thing that it has to do with? What is the thing that it has to do with? Or you can tell me that what is the main reason that because of that it does not have that much of electronegativity. I'm asking this question because, yeah, I'm asking this question because this is the thing that I have discussed already. I mean, it has but low. It has 4 valence electrons. Yes, I know, I understand. It has 4 electrons. It has but low means I don't understand, I mean, but I'm saying that this phenomenon or characteristic of an atom, I already have discussed in the atomic structure, and that is why I'm asking the question. Be sure that any question I put forward, oh, there will be your test will be next week, yeah, week 5. Your test will be, oh, forgot to remind it this week announcement, but I think I talked about it last week classes. So I'll go and modify this announcement. Your test will be next week. I'll find a time when it will be, but your test will cover all week until week 4 lecture and tutorial and lab, everything. Okay, so yeah, I'll go and amend it right away. And so I'm saying that whatever the question I put forward or put in, be sure that it has been already discussed in the class. So the answer is very simple actually. Audrey says it is related to the ionization energy. Very close, pretty close, pretty close. Thank you. Thank you. Thanks to everyone, those who have tried. But the thing is, carbon, where is my P table? Carbon just next to boron, it has 6 protons, right? 6 electron as well, but 6 protons. Whereas oxygen and chlorine, they have higher number of protons. That means they are much capable, their nucleus, I mean, oxygen or fluorine or chlorine, their nucleus is much dense, much higher. 3 more, it does not mean that, oh, only the 1 more proton, 2 more proton, 3 more proton. No, even 1 more proton makes it a bit much heavier. All right, the proton is very heavy. So, oxygen has 2 more protons, and the shell's electron cell size is the same size. Electron cell size is the same size. That means hold on, just there's supposed to be a whiteboard here. Why I cannot see the whiteboard? So since the cell size is same, with a higher or stronger inside the core, that means the nucleus, oxygen can attract more. But carbon, it has 4 electron, it needs 4 electron, but it does not have that much power to attract more electron. That is why its electronegativity is low. And this is to do with the nucleus. I already discussed that, I'm saying. And also the shielding effect, right? All those things, it should be considered in. Anyway, so now go back to the formation of covalent bond. And that is why carbon does not have that much electronegativity. That means it does not have that much capability to take all these electrons. So it will only share 4 electrons with 4 hydrogen or 4 chlorine. All right, or 4 any other 4 electrons that can give, or maybe 2 oxygen. It can share the electron with 4 electron from 2 oxygen, because oxygen can form 2 bonding. So oxygen can give 2 to 4 electrons from 2 atoms. We'll see later on. So that is why carbon will be formed. This carbohydrate or CH4 and all those things. And this is how the bondings are made. This is the methane gas that we use for our cooking purposes. All right, this is for our cooking purposes. Usually it is a natural gas. It's a natural gas, but if it is in the bottle, like we use from Petronas or Shell, the bottle, right? We bring it. That is low in methane but high in propane and butane. Propane mostly, and that is why that is much heat content is higher in the bottle gas than natural gas. Anyway, so yeah, this is by what do you say? This is the covalent bonding. All right, the formation of covalent bonding when they are in association with each other. So according to Lewis structure, oxygen and oxygen both are similar. Both of them are same. Both of them have strong, equal energy. Both of them are strong, equally strong. So equally strong, so that they cannot bully other. So what they will do is they just share electrons between themselves. So since they are two same thing, there will be covalent bonding. And this is true for all diatomic gases: nitrogen, nitrogen, oxygen, oxygen, hydrogen, hydrogen, then chlorine, chlorine, fluorine, fluorine. All those atoms should be covalent bonding, right? So H2, be sure that is the covalent bonding. Cl2, it is a covalent bonding. So N2, it is a covalent bonding. When the same atoms together, that is a covalent bonding. And that is how they are very stable. They are quite stable in that way. Typical bond for main group elements, hydrogen and group 7A. So of course, this is HCl. What type of bonding will it be, do you think? Isn't it ionic bonding? Do you think it's ionic bonding? I cannot see the chat box anymore. Do you think that it will be a covalent bonding or it will be a ionic bonding? If there is an energy, what do you call it? Difference, electrostatic energy difference is more than 2, it will be ionic. If it is less than 2, it will be covalent bonding, ionic covalent or pure covalent or non-ionic covalent. So we will be seeing based on our calculation. So to know exactly what type of bonding it will be, we have to know the electronegativity from each of the elements that are involved in the bonding. All right. Okay, so group 7A, group 6A, because 7A needs only one electron. 7A means 7 electrons already at the outer shell. 4A means 4 electrons at outer shell, they need another 4 to become 8. 5A, they have 5 electrons outer shell, they need another 3 to make it 8. 6A, they have, here, 6A, they have 6 electron outer shell, just need another 2 to make it 8. So in this way, we see that carbon and hydrogen, they are making covalent, covalent bonding. Carbon and chlorine, they are also making covalent bonding. Nitrogen, hydrogen, their electronegativity difference is not that high, so it does not qualify to be a ionic bonding. Same goes for hydrogen and oxygen. Their difference is not that high, so it's the covalent bonding for HCl as well. But if it were sodium chloride, it would be ionic bonding. So just because hydrogen, you don't, think that since hydrogen is also 1A, so it will produce a covalent bond. No, because hydrogen is different. Okay, so another thing is oxygen and oxygen. Of course, it is a covalent, pure covalent bonding. There's no doubt. Nitrogen and oxygen as well. There is a covalent bonding because they are just neighbors. So their difference, electronegativity difference is not that high. And they are neighbors, so they are in very good condition. So they do not want to snatch one another. Oxygen and carbon. Same goes for oxygen is electronegative, of course, but carbon is not that like sodium. It is not less electronegative like sodium, so they are also similar electronegativity, and that is why they will be. Now, since I'm here already, I just want to mention one thing, that the assignment that will be given to you, you will have to discuss. Are you listening? Chen Liang Teo, are you there? Chen Liang Teo, are you there? All right. Eman, I don't know whether I'm pronouncing it correct. Yemen, are you there? Okay. And then Lee Yun Shir, not sure. Lyeyuen. What is your name? I mean, how do you pronounce that name? Are you there? Keshwan, you there? Ezra, Gabriel. Okay, all right, good. Most of us are listening then. So, okay, I wanted to say that, okay, the assignment that will be given to you will be based on the structure of atoms and then molecules, formation of molecules, and their properties in a magnetic field. Okay, how would be their structure according to the valence bond theory, VBT, and molecular orbital theories as well. So you have to go and search for these two things, molecular orbital theory and valence bond theory. There are lots of resources online you can find. Of course, you can, if you want to find, you can find from the library as well. Another thing is that their vibration properties will also be given. I mean, will be, you need to discuss, right? So, for example, this oxygen and oxygen, they will have vibration. All right, they will have vibration, and external magnetic field, they will behave because of this vibration, they will behave differently. Depends on what is the strength of the magnetic field or how long it has been exposed to. So depends on that. Now, oxygen, how they are able to vibrate. See, I need to delete it now. Okay, good. Oxygen, how they are able to vibrate. There, I'm just quick way, I'm telling you that these two oxygen, they can go away from one another, right? They can go away from one another. Another thing is they can come together same way. Actually, they will be vibrating like this, right? And this is two types they can vibrate. For carbon dioxide, sorry. For carbon dioxide, they can go, of course, both way. They can go and come back further away from this carbon molecule, carbon atom, and then come back. Also, they can vibrate like up and down. This oxygen can vibrate up and down, keeping the carbon constant there. You see that oxygen is going from like this, like a spring, like it is happening like that, and also it is vibrating. Both of them are vibrating like that. One is that. Another is in rest. When is up and down, one oxygen atom can go up while the other is going down. So like this vibration, it can happen. So there are different ways that vibration can occur, and because of their vibration, they're in the electric field, they have different properties, and it will be a thing for you to discuss in your assignment 1. All right, so now we are going for the Lewis structure. How do we draw the Lewis structure for molecules? All right, not for atoms. For atoms, we don't need to. No, I'm not saying that no need to, means it's more important for molecules to draw the structure, because for atom, we already know that we just need to put the dots for this, what do you call it, all around it, so that to represent the number of valence orbital electrons. So drawing a Lewis structure is arrange the skeletal structure of the compound. Skeletal structure of the compound, that means the skeletal is hydrogen and chlorine. It will be the skeletal for that, and the less electronegative one in the center. The less electronegative always should be at the center, and this is important. Less electronegative one. So among them, which one is, of course, for binary compound, we don't have to bother. But if there is more than one, two elements in it, the less electronegative one should go in the center. All right, because more electronegative one, they will take 1 or 2, maximum 2 electrons, mostly 1 electron they will take. Fluorine will take only 1 electron, never 2. So they can only take 1 electron. That is why if they go inside the center, you cannot probably make any structure of that. You will be lost. So less electronegative ion should go into the center of that. Afterwards, we need to count on the total electrons, valence electron in fact, of all the elements that is involved. So for carbon, it will be 4 elements, so there will be 4 electrons for carbon. For chlorine is more electronegative, so we are not considering it. And for carbon is 4A, but for nitrogen is 5, right? So there will be 5 electrons in here, at the outer shell. And number 3 is draw a single covalent bond, just like I drew it here. Hydrogen, and in between hydrogen and chlorine, there is a single bond is here, and this single bond represents 2 electron. Represents 2 electron at the end of the bonding. So one dash line means, let's say, sodium and chlorine. Sodium and chlorine, between sodium and chlorine, this one dash line is representing 2 electrons. So let's, for visualization purpose, I put 2 big dots here. So this is 2 electrons at the between them. So one dot dash showing that it is 2 electrons inside. The remaining of the electron should be all around it. So sodium will have another 6 electrons for this case, 2, 4, and 6. And usually these dots are given in pairs, right? So in fact, instead of doing like this, we give this electron, we show the electrons in pair, because electrons stay in pairs. We have seen it, right? In p orbital, 2px, 2py, 2pz, there are 2 electrons. So that is why we'll show the 2 electrons in a pair. If it does not altogether makes a 8 electron. So this is 2, this is 2, this is 2 electron, and chlorine will also have 6 electron at the outer side, 6 electrons. Let's say here is 2. So altogether it will have 8 electrons. So 2, 4, 6, and then in between these 2 is 8. And this 2 is shared by both sodium and chlorine. So this is a common, we should, when we count it, we will count the common number for everyone. Sodium has these 2, chlorine also has these 2, 2, 4, 6, and then 8, 2, 4, 6, and then 8. So this is a common, so all now sodium and chloride becomes octet. They filled up octet. But if we see that it is not finding the octet, or it's not getting the octet, we'll try to make 2 or 3 bonding. 2 bonds or 3 bonds. 3 bonds means there is, what do you call it? 6 bonding are there. So just for nitrogen, there are 6 bonding in between them, and it does not fill octet, right? So there are another 2 electron there will be paired on each of the nitrogen, and in this way it will be octet filled up. Of course, at the end we need to count on if it is same as we added up. All right, we are going there soon. Okay, we will have a Menti question soon, but after we finish these few examples. Write the Lewis structure for nitrogen trifluoride, which is in which all 3 fluorine atoms are bonded to nitrogen atom. So here at the beginning we have shown you that nitrogen is in the middle. Fluorine is very high electronegative, so it cannot go in the middle. Nitrogen is at the center, and then it is surrounded by fluorine atoms. So 3 fluorine atoms are bonded to the nitrogen atoms together, and now we have to count on total valence electron. There are 7 valence electron for fluorine, right? It is there, but I just want to draw for you to see. So there are 6 and then 1 electron here. Same goes for this fluorine as well. So 2 electrons, 3, 4, 5, and 6, and then another one is 7. So this 7. What about nitrogen? Nitrogen is 5A element, so it will have 5 electrons as well. So 2, 3, 4, 5. So what we'll do is I will make this bond together, and it will go and bond here as well. In this way, I will make them. Oh, before that, I need to count on the valence electrons. So nitrogen has 5 electrons at the outer shell, and fluorine has 7 electrons in the outer shell, and there are 3 fluorine atoms are here. So all together is 26. After we have done all these things, I have to make sure that there is a total of 26 electron here. Total. So 2, 4, 6, and then it is 2, 8, right? 8. This is 8 as well. This is 8 as well. Okay. This is 8. So 8 plus 8 plus 8, and then this rest of 2, right? So this 2 is forming altogether is 26 electrons. Nitrogen, whenever there is a nitrogen molecule element in your octet Lewis structure, take extra care because this is quite problematic to some extent. Sometimes students say that, okay, there are 2 electrons, why don't they make another 2 bonding? Another 2 bonding, let's say X and Y, whatever this can be. No, because if in this case it has 6 electron for all these 3 bond with fluorine, it has 6 electrons, but if it is has another 2 electrons here, so 8, and then 2 electrons here means 10. Nitrogen cannot go beyond 8. It is a group 5 element and 3 period, second period. So it is a very difficult. It will not form, and this another bonding. Only it will stay as a lone pair. Just as a lone pair it will stay, and because of this lone pair there is the bonding shape also becomes distorted. These shapes also become distorted because this lone pair on the nitrogen, all right, the lone pair on nitrogen is shown in this way. This is the electron cloud. Of course this is a 2p electron, so this 2p electron, it is taking a big space here, not only here, I mean it is a big space, it is taking here. So this fluorine bonding with them, it will be like distorted in a way that it can maximize or it can disperse the most, so that they have a minimal interaction between this electron cloud and this electron cloud. There is the electron clouds, right? These 2 electrons are staying. That means this is the electron cloud. You can find the electron there. And also this bonding between fluorine, there is 2 electrons here. So this is also electron cloud here. Same thing, electron cloud. So 2 electrons are here as well. And same thing goes for here as well, the electron clouds. All right. So this is fluorine, this is fluorine, this is fluorine. So all together, it is, you know, it will be displaced or distorted in a way that it does not interact too heavily. Just this is an extra thing. You will need it in for your assignment. Okay, write the Lewis structure for nitric acid. After this, I will probably, and let me check. This interview. After this, I will move to probably the Menti question. What's the time now? I have to finish today. Not sure if we can finish. Right, the Lewis structure for nitric acid. So HNO3. Which one has the lowest electronegativity here? Can anybody tell? Which one of them has the lowest electronegativity here? If we go to the periodic table, right, and let's see the hydrogen has electronegativity of 2.20. Where is it? Okay, nitrogen has 3, oxygen has 3.44 electronegativity on a scale. All right, this is just a scale to show. The thing is, hydrogen and lowest is hydrogen here, right? Let's see that hydrogen is lowest, 2 point something. I just 2.4 or something, I think. Nitrogen is more, oxygen is even higher electronegativity. So by definition, that what we learned, that hydrogen should go in at the center, but this is an exception. Again, sorry to say that hydrogen cannot go into the center for a Lewis structure because hydrogen can make only one bond. So if we put it in a center, we cannot make an atom. Can anybody confirm me that, can you see that I'm writing on the, or I'm drawing on the slide? Okay, good, thank you. Okay, so hydrogen cannot go in at the center because it cannot make more than one bond. If it cannot make more than one bond, it is already stuck there. There is no way that we can make another molecule. Only one one bonding, make a molecule, but one bonding molecule, very simple molecule you can make if it goes in the center. So what should you do? We will check, we'll choose the next lowest electronegative element, which is nitrogen. So we put nitrogen at the center. And then we put nitrogen in the center, and then of course surrounded by oxygen, and then hydrogen is coming along. So altogether, what we have to do is we have to find out the total number of valence electron for all of them, including everything. Oxygen has 6, sorry, oxygen has 6 valence electron, nitrogen has 5, and hydrogen has 1, only 1. So altogether, it is 5 plus 3 times 6 means 3 oxygen and 6 each of them, and plus 1 is for hydrogen 1. So altogether is 24. When it is there, we just draw. It is one step jumped here. So we should draw it first, 2, 4, 6, 2, 4, 6, 2, 4, and then 6 in this case. So oxygen, nitrogen is having 5 electrons, right? Nitrogen has 5 electrons. So what it is going to do is, where is the another 2 electron? You may ask that where is the another 2 electrons here? It is not, I'm not showing you the another 2 electrons, right? So yeah, all of them are having the octet filled up. We can see the 2 electrons here, 4, 6, and 2 electrons from this bonding are shared by nitrogen and oxygen both. So oxygen is filled up with their octet. This oxygen also filled up with their octet. This oxygen also filled up with their octet. Hydrogen filled up with octet. Because it only can make 2 electrons at the best, hydrogen. So they have taken already 2 electrons, this bonding, 2 electrons from this bonding, right? So this oxygen is 2 electron here, 2 here, 4, and then 2 here, 6, and 2 here, 8, right? So altogether is 8 electrons for everyone. But oxygen, nitrogen, I did not show that electron yet. So if I don't show this, if I don't, then it does not have the octet. Nitrogen does not have the octet. Can you did you notice that it is 2, 4, 6? It has only 6 electron in together, right? So what we'll do? What should we do? This electron will come here. It will be generous enough to come here and produce a double bond, because this oxygen, it already has 2 electrons, which is just sitting there, not used. So it will be donated by oxygen to nitrogen. Okay, from oxygen to nitrogen to form a double bond. To form a double bond, so that nitrogen can have some share and can be restless. So it can be more stable in that way. Otherwise, it does not having it is not having the electrons in it. So this bond, this double, electron will have and come in here and produce a double bonding. And that is how the double bond is being formed in between nitrogen and oxygen. But if we make this is a double bond, what will happen? Any idea? Can anybody tell me what will happen? If we make this double bond to oxygen and the nitrogen here as well, what will happen? Any idea anybody has? Gabriel is typing. 2 lines. Yeah. So can I make another 2 lines? Can or cannot? How many of you say can? How many of you say cannot make another 2 lines? Cannot. Okay. Or you says cannot. Let's wait for another 2 minutes for 2 students to reply. Ainin and who is typing? And after that, I will go to the Menti question. It cannot form a double bond. Rather than waiting, it cannot form another double bond. If it forms another double bond, what will happen? You see that here is 2 to 4 electrons. Here is 2 to 4 electrons. So altogether 8 plus 2 electron, 10. Nitrogen cannot have more than 8. It cannot go beyond 8. Remember this, okay? So it will not form 8 electrons. I mean, this double bond, 2 double bond, it cannot make. Okay. Another thing is, all right, if it does not make this double bond, can it make a double bond here instead of making a double bond there? Let's say I do not put the double bond here, but I put a double bond here. Is it possible? What do you think? Is it possible? No, it's not possible. Although you didn't reply, it is not possible because in this case, oxygen will have expansion of octet. I mean, it will have more than 8 electrons. So 2 to 4 to 6 to 8 and plus 2 is 10. Impossible that oxygen can go 10. Cannot. So that it will not be favorable as well. So only this is the double bond option. But there is another, don't listen only half, yeah? So this is one structure. This is one structure, and this is hydrogen is here. And there is an oxygen atom here. What will happen if it does not form this bond here? It can form with this. So that means this double bond can be here or here. Either place it is possible, and it is very okay to be there both. In one place. It not necessary. Both of these oxygen are identical, same oxygen. There is no partiality. There is no favor to one or another one. So nitrogen can form bonding to any of this oxygen, and in fact this double bond will jump from here to there, which one we call resonance. We are going to that slide later on. Now we just look at the carbon, one ion now. We look at the ion, not a molecule at all. That reason. So it will be an ion, and it is the carbonate ion. So as usual, carbon should go in because it is the less electronegative, and it can also form many bonds together it. So there is the total number of, for here there is 2 electron. It shows that it is 2 electron it has, right? 2 electron, negative means extra 2 electron it has. That is why it become negative. Carbon is 4. We already know that carbon has valence electron force 4. Oxygen has 6, sorry. Oxygen has 6 and 3 oxygen atoms. So 3 times 6 plus this 2. Plus this 2. So 4 plus 3 times 6 plus this 2 is 24 electrons altogether. And then if we are making this bonding, we should be always careful to make it 24 altogether. So now we see that oxygen is 8, this oxygen is 8, this oxygen is 8, but carbon is not 8. Carbon is only 6. So what should we do? To make it 8, we will make one double bond here, so that it will be 8 electron. Of course, we will move from here to make it 8 in this way. Okay. And in this case, if we do so, we will see that we need to add another 2 electrons to make it balance, or to make it octet for everyone, right? Or we need to loan these 2 electrons so that it becomes stable in that way. And that is how it will be achieved. Octet is achieved for all of the elements, or all of the atoms here. Formation of covalent bond, valence bond theory, VBT. According to the valence bond theory, also known as localized electron pair theory, we will not go much into it, but just to introduce you that the orbitals bond is formed when orbitals from 2 different atoms overlap each other. So let's say this is s orbital, one s orbital. This is one s orbital as well. So when they are forming the bonding, they are coming together and become infused to each other, right? They are becoming infused to each other, and slowly they are together, and this size of the new bond is very similar to the original S, but not exactly the same. Okay, so this is how they are forming the valence bond theory. This is how we can explain the structure of the atom or structure of the molecule by valence bond theory as well. Energetic of covalent bonding. Similar way it goes, the lowest number of potential energy will be the better for stability, right? And again, if it is very close to each other, that means it does not allow everyone the minimum room or space. It is very repulsive and it will not form a bonding, or it will not be a strong bond. And another thing is, if they are very apart from one another, also it will not form a bond, but they are just nice when they are at their radius distance, just their neighbor to each other, they are good. It's very similar to our human nature as well, right? So sodium chloride and carbon tetrachloride. Sodium chloride is a ionic matter compound. Carbon tetrachloride, however, is a covalent liquid. Covalent bonding here. So the difference between them, you see, quite solid because of their ionic carbon. Here is carbon. Here is chlorine. 4 chlorines are there, right? There are 4 chlorines are there. Here is carbon. I'm sorry, here is sodium and 1 chlorine is there. Still, they are making solid. Their temperature is 801. Their molar heat fusion is 30.2. Boiling point is 1400. And if we go in this way, we see that it is very, very low because they are covalent bonds. Okay, and here the types of different bonding. If we take it maybe metal plus non-metal, it will be ionic bonding. Okay, if it is metal plus non-metal, it will be ionic bonding, like potassium and chlorine, sodium and chlorine. and rubidium or yeah, cesium and chlorine. It will be metal, I mean ionic bonding. Non-metal plus non-metal, oxygen plus oxygen, hydrogen, oxygen, hydrogen, chlorine. So this type of bonding, they will be covalent bonding. But the problem is, okay, metal plus metal is the metallic bonding. We'll see later on. So there is no 100% pure ionic bonding, and most covalent bonds do not have equal sharing of electrons. So that means there is no 100% pure ionic bonding. That means only taking and not sharing. Is not like that. Everyone shares, but for ionic bonding, some of them takes more. And that is why I'm saying that if we just say that, okay, snatching the electron or taking it forcefully, it's not the right way to describe. Rather, 45%, I mean, taking 85% or 90% and 10% someone, and the other one is taking. So this is way of bonding, and that is the strong bonding. That's how this is possible. And another thing is, and most covalent bond, even the covalent bond, that's why I was saying that 45-55, it is not equal sharing. Somebody will take a little bit more, somebody will take a little bit less, and both of them are stable. As long as they're stable, they are happy. Taking more or less, it doesn't matter, they are happy. And that should be the human nature as well, right? So electronegativity and bond polarity is electronegativity is going from this side to this side high. This is not counted, and it is decreasing from here to here. It is decreasing. So in this way, electronegativity, we know the fluorine is the highest electronegative, then oxygen, then chlorine, nitrogen, phosphorus, all of them have negativity. So before we move in to the bonding and polarity, just go to Menti question. Please go to the Menti question, menti.com, and I will give you this time only 5 minutes break, and this will be your Menti question code. This is the code 99078838. Please go and do the Menti question now. Okay. Oh, sorry, this one shouldn't be a question because I haven't gone through this yet. Sorry, I haven't gone through yet. So yeah, sorry. Boarding should be closed. Uh-oh. One minute. There is one, but it's very easy question. I don't want to ask this question for you guys. there is one question I have, but it will be for the Lewis structure, what I think we need to go more detail into it, so I'm not going to ask that question. Anyway, we will be taking maybe another 5 minutes break. But before I go to the break, just give you some thought to some task to think. So probably you will have some time to. The Menti question that last class I asked which of the bonding takes higher energy to break. Nitrogen, oxygen, chlorine, and HCl. Most of you, 4 of you, has voted for HCl and is good, which will take more energy to break. For nitrogen, oxygen, chlorine, they are covalent bond, so easier to break for them. And yeah, okay, I cannot find anything now, so please go for a 5 minutes break. I'll come back after 5 minutes. Okay, I'll talk to you later. Hello, I'm back. There is a question from Gabriel. So is it possible to see which question we did wrong for the quiz? I mean, after the due date. I think it was supposed to be viewed after the due date. If not, is it not? Muted. I mean, you cannot view what question was asked and what question was. Okay, I'll check the settings once again. Usually I allow students to view after the due date, only for their question they have missed it. Probably, I don't know, only can see how many question I correct. Oh, okay. Thank you for the feedback. I will change it. I will try to amend it as so that you can see your question. All right. Okay. Thank you. Okay, now go. We have only 10 minutes to finish. 15 minutes. So here we are, the electronegativity and bond polarity that we have seen. So the more the electronegative bonding, the electronegativity is increased. The higher the electronegativity, the more the bond polarity. The difference between it, like sodium and fluorine, their electronegativity is 0.9, 0. Sorry. So this electronegativity is 0.9 and then it is 4. So the difference is more than 3.1. The bond polarity is very high. Polarity means they will be dissociated in positive and negative charges. So the fluorine will try to take all the electrons, I mean 1 electrons to each side, and sodium will be deprived, or it wants to be deprived anyway, so that it will be partially positively charged, it will be fluorine will be partially negatively charged, and then the bond will be very much polar. That will be polar bond. And what do we do with the polar bonds or polar bond polarity? That is how we can detect whether this type of material or element will have charge on it, or whether they will behave in a certain way in liquid or aqueous solution, or whether they will have very much what do you call it, reactivity. Their reactivity, we can also get some idea about their reactivity, what type of reactivity they will have. All right, so those who are not polar, those who are not very stable, they do not want to share they're stable, they don't usually do for reaction, but those who are polar, they are very active. So in this way, electronegativity increase, that's why I draw it. It goes up from left bottom corner to top bottom part. The electronegativity will go up, and also it will go up from bottom to up. All right, anywhere you go from bottom here, it will decrease in this way. So that means if the inverse is true, it will increase in this way. Anywhere you go, it will increase. Of course, this is a noble gas, so we discuss it later. Now, bond polarity. If we see that lithium fluoride, cesium fluoride, potassium fluoride, cesium chloride, potassium chloride, of course, here is also bond polarity. This is the highest bond polarity. That means they are very much ionic bonding. They have a very different in polarization bonding. They are, to some extent, you can say, it's not that polar. It's still polar, but not that polar. And here you see that hydrogen iodide, hydrogen chloride, hydrogen bromide, or hydrogen itself, right? So there, the difference is, sorry, here, sorry, hydrogen will not be there. Hydrogen will be here. It's 0. Hydrogen to hydrogen, oxygen to oxygen. They have no difference between them, polarity. So they are 0. So electronegativity differences are based on this curve. We see that it is very high in this part. Then it is mostly ionic bond, more than 2. I drew it around 3, where it was around 3. But yes, we in this way, in this region, more than 2 is ionic bonding, and less than 2 is covalent, sometimes polar covalent bond. Okay, so this is the pure, or not pure in fact, these are the towards the covalent bond, or only hydrogen, oxygen, nitrogen, when they're together, they are very much pure covalent, we can call. And this is a bond which has electronegativity difference between these atoms are less than 5, but more than 0.5. Okay, so they are considered that they are polar covalent bond. All right, they're they're covalent bond, but still they have the polarity towards. They can be differentiated in positive charge and negative charge as well. So 1.6, 1.7, 1.8, or around 2 is the landmark or benchmark for the polarization. More than this is ionic bond. Less than this is covalent bond. Of course, covalent bond will be polar covalent or non-polar covalent. So here is the table that more than 2 is ionic bond, 0.5 to 1.9 is polar covalent bond, 0.0 to 0.5 is towards the pure covalent bond. Okay, so now, sorry. See, there's some of the basic bonds as ionic, polar, covalent, or covalent. The bond in hydrogen chloride, if we see the electronegativity difference is 0.9, so it is a polar covalent bond. It's not a pure covalent bond, it's a polar covalent bond. It's not an ionic bond as well, it's not more than 2. And it's a polar covalent bond. Potassium and fluorine. Potassium is 0.9, 0.8, and is 4, so it's 3.2. It's a purely ionic bond. Potassium iodide is purely ionic bonding. And carbon-carbon bond between H3, CH3, what is this? CH3, CH3 is an ethane, right? CH3 we can write in this way so that it will be easier for us to understand. CH3, CH3. So it is ethane. So this carbon-carbon bond between them is 0, non-polar covalent bond. It's a pure covalent bond. All right. But how long do we have? 10 minutes. So when we are saying the pure covalent bond, let's say this is carbon. This is carbon atom. Very simply, carbon-carbon atom. And they are sharing the electron, right? 4 electrons they are sharing to each other. They have 4 electrons as well. So what are they doing is they are making the bonds between them. Let's say 2 bonds or 3 bonds, something like that. And of course, 1 bond is with hydrogen, or let's say that carbon-carbon is sharing 3 bonds to each other. We'll see more about it in organic chemistry when we move to organic chemistry, but okay. So why we can say and cannot say that it is a pure covalent bond and 100% pure covalent bond? Why we cannot say that? Because from the VBT, that is why VBT is needed. Actually, valence bond theory is needed, right? So the electrons are moving around in a very simple schematic way that we are showing. Very simple graphic that 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons, right? Carbon and carbon it is having. So what at some point, let's say that for a fraction of a second, this this carbon has all 5 or 6 electron, and this carbon has only 3 electrons. Out of these 8 electrons, one carbon at a fraction of a second is having 5 or 6 electrons at a time. Another one is having 3 or 2 electrons at a time. Right? So the thing is interesting that this carbon is heavy on having more electron at that moment of time. So in this case, it will be negatively charged, a little bit negatively charged, whereas it will be a little bit positively charged. So there is a separation as well. If we look through the valence bond theory, molecular orbital theory will give you a better perspective, but valence bond theory is as good as well. So some moment, that is why quantum mechanics we should learn, but here is not the place that we should discuss. If there is sometimes when they are rotating, they are shifting and then they are moving around. So in some case, one carbon has more than 4 electrons or 5, more than the other. In this case, it will be a little bit positively charged. Sorry, negatively charged. So this is another problem that we cannot say that pure covalent. Sometimes they are is covalent, but at some moment they can be positive, simply negative charged. The given electronegativity values of aluminum, fluorine, and all those are given here in this table. So we have to arrange it increasing that order of the ionic bonding, and you can see it just by differentiating, getting the electronegativity difference between them. Aluminium fluoride as well is having the difference, more electronegativity difference, so that is why it will be more towards polar bonding. Lewis structure and octet rule. Again, we will be talking more about Lewis structure and octet rule, and I don't want to start now, but for the next tutorial, I think I'll talk about it. If not, then I'll finish it in the next class. And if you have any question today, I'm almost done. If you have any question, if not, then let's go to that Menti question. Now we can figure out what will be the answer for this. Okay. Oh, not this one. Oh, this one will be here. Yep. Okay, please go into the menti.com. And here it is, the link for you. Not link, actually the code for the menti.com. Same code 99078838. Now you can vote it, right? You can vote, and I'll share the screen for you as well. Okay, so which of the following is correct? Lithium hydride is a polar covalent bond. Sodium iodide, NaI, is a covalent bond. Carbon nitrogen cyanide is a metallic bond, and carbon monoxide is a polar bond. So yeah, show the, please vote. You have only a few minutes to go. Maybe I'll put 2 minutes for it. I cannot extend more than 1 minute, so after 1 minute I'll put it. Any question anybody has? Okay, 1 minute to go. 4, 4, 8, and 9. All of us has voted already. One minute to go. 2, 4, 6, 2, 4, 3, 5, 10, 11. 11 of us are here, but only 9 votes so far casted. So I'm waiting for another 2 because there is a good tie between lithium hydride and carbon monoxide. So another 2, where do you want to vote? Do you want to vote one each other to make it a tie, or you want to go for one side? Just one vote will make your friends win. 10 seconds. 10 seconds. Done. Voting closed. So your friends didn't help you. Lithium hydride is a polar covalent bond. So carbon monoxide is a polar bond actually. Lithium hydride, you see that carbon nitrogen is not a metallic bonding, of course, because carbon and nitrogen both are non-metal, so it cannot be a metal bonding. Sodium iodide, Na, is a covalent bond. It is not a covalent bond because you have already understood that sodium and iodine, they are metal and gas. So iodine is very much electronegative compared to sodium. So that is a ionic bonding should be. And lithium hydrogen, if we go and look at the periodic table, if we go and look at the periodic table, we see that lithium has a negativity of 0.98, hydrogen has 2.22. So in this case, it is 1.1, the difference. Where is my slide? Yeah, it is in this case 1.11. So that is the difference is 1.11, and by definition, it is a covalent bonding towards the polar covalent bonding. But carbon oxide is carbon is, let me see how much the electronegativity of carbon is 2.55 and oxygen is 3.44. So this is the difference. Hold on. The difference between them, where is Yeah, so difference between them is more than 1.1, and that is why it will be more towards the polar bonding. Okay, it is more towards the polar bonding than lithium hydride. All right, so do you have any question to say, ask for today? Anybody disagree? Anybody? If not, then I consider everybody agreed. No. Okay, so I'll see you tomorrow during the lab at 12 a.m. 12 p.m. Sorry, 2 p.m. Malaysia time. So yeah, Gabriel is typing. Yeah, okay, see you tomorrow then. Okay, take care, bye-bye.